and I've recorded this twice now. I'm tired. So let's just get through it. Primary productivity. This week, we're going to be talking about the recycling of energy through an ecosystem. We've already talked about the recycling of nutrients and minerals. Now we're going to talk about how energy cycles through an ecosystem. So it's our first little baby bit of math. So primary productivity is the rate that solar energy is converted into organic compounds via photosynthesis, which means how much energy is available in plants after photosynthesis. So we think about this in kilocalories, which is energy, per meter squared, which is the amount of space, in a year. So how many kilocalories in a meter squared in a year are available to the ecosystem? So basically, you're looking at the rate of photosynthesis of all the producers in an area over a given period of time. And usually it's meter squared over time. So because the photosynthesis directly leads to growth, you can almost think about how much the plants have grown in an area over a given period of time. So if you want to think of it that way, you can think about how much plant growth is available, how much plant nutrients are available in that region. If you have high primary productivity, that means you have lots of plant growth, which means there's lots of food and lots of shelter for organisms. If you have low primary productivity, you tend to have low biodiversity. So high primary productivity usually leads to more diverse ecosystem versus a low primary productivity, which is going to be something that's very low in biodiversity. So in order to calculate primary productivity, we're going to look at not only the amount of energy that's created during photosynthesis, but we also have to look at respiration loss. And respiration loss is how much energy plants use up during their little plant life. So that means, plants have to grow, they have to reproduce, they have to grow leaves, they have to repair things in their cells. So they have to go through respiration for themselves. So how much energy is available after they've gone through their, daily cellular life, their plant life. So think of that respiration loss. If we're thinking about primary productivity as like the paycheck, the amount of energy that's available, so think of your respiration loss as the taxes that are coming out of the paycheck, okay? Gross primary productivity is like how much sunlight energy was converted into sugars through photosynthesis. That's the total amount that was in the area. So that's like how much do I make per hour times how many hours I worked. So I make $10 an hour, I work 20 hours, I make $200. That's my gross paycheck, okay? But we have to take out the taxes. We have to take out the respiration loss. So net primary productivity, or your net paycheck, net primary productivity is the amount of energy that's left over after the plants have respired and utilized that energy and paid their taxes, right? So your net paycheck is, okay, I made $200, but I have to pay $20 in taxes, so now I really only make $180. So when we calculate net primary productivity, we're going to say the net primary productivity is the gross primary productivity. So the total amount of photosynthesis or glucose that was created minus the amount of glucose that was utilized to let the plant live its own life. Some of that is lost as, think of it as lost as heat, okay? So if you take a look at this diagram here, so 99% of the solar energy is reflected or passes through producers without actually being utilized. 1% of that is actually captured through photosynthesis and creates gross primary productivity. 60% of that gross primary productivity is used by the plants. The plants are using all that energy. 40% is what's left, right? So 40% is like from that 1%, 40% of that 1% is what's left. Okay, so you have to think about how the plants are using that energy. So 40% of that is left. Only 1%, like I said, 1% is captured and converted to photosynthesis. So only 0.4% of the sunlight or the solar radiation that's coming in is converted into biomass or usable energy for an ecosystem. So of the 100% of sunlight that comes from the sun, only 1% is actually absorbed, and only 40% of that 1% is actually available to the rest of the ecosystem. Some are more efficient. So some have a higher net primary productivity than others. What we tend to see is that the wider biodiversity it can support, that means it's generally more productive. Okay. So try to think about, write down in your notebook, which ecosystem do you think is going to be the most productive? So the have the highest productivity versus the lowest productivity. If you take a look here, it's interesting because terrestrially, I think I made that word up. Swamps and marshes are actually the most productive. And then we have rainforests and forests. Obviously down here, the tundra, the desert, those are going to be the least productive. And then coral reefs, like we said, the rainforests of the ocean, right? And then salt marshes right up there, similar to swamps and marshes, have the highest primary productivity per year. Remember the limiting factors, the availability of water, the temperature, the nutrients, those are all things that lead to high productivity. Yeah. Okay. So like we said, the desert, the tundra, and the open ocean, we said those are going to be the lowest. The coral reefs, the salt marshes, those are going to be the highest in terms of their primary productivity. All right, so trophic levels and the rule of 10%. This is definitely something that you've learned before. I keep moving my little face around because I'm trying to make it so you can see all the words on the screen. But remember that the rules of thermodynamics say that matter and energy can never be created or destroyed. They just change forms. So we talked about the biogeochemical cycles. Those all get recycled and returned to the soil, the atmosphere. The energy from the sun is then converted into glucose. So the law of conservation of matter and energy says that all of these things are just going to be recycled and reused. Food webs are how we see the conservation of energy within ecosystems. When a rabbit eats a leaf, it gets energy from that leaf and then stored in the rabbit to be used later. And then if something comes along and eats the rabbit, same thing happens. The second law of thermodynamics is that every time energy gets transferred, so even though it can't be lost, it's transferred into another form, some of it's eventually going to be lost as heat. So if we look at some of these calculations that we'll be doing later in the year, in a power plant, 35% of it can actually be transmitted, energy can actually be transported to the users. And even from there, you're going to lose even more. And some of that is even going to get lost as energy and heat. So you're really not, some of these things are not very efficient. In ecosystems, however, they're relatively, you lose a little bit less. It's not as drastic as that image that was just showed. So the amount of usable energy always decreases in a predictable way as you move up the food chain. It's called the rule of 10% because what you start with, you get 1,000 joules of energy, of light energy, 1,000 units of energy. And we said most of that, only 1% is going to be available for food, okay, as a producer. So 10 joules of energy, and then only 10% of that is going to transfer into the next food web, into the next trophic level. So available energy is going to decrease with each step. So remember that trophic levels are the eating or the area in where the organisms survive for their nourishment. And we use trophic levels to model how energy moves through an ecosystem. So an energy pyramid, it's going to show you visually how much energy is lost. So here's your producers. They should be the largest level of energy. And then energy is going to be lost at each step. So some energy gets transferred, some energy gets lost over here. So the rule of 10% is that only 10% of the energy from one level makes it to the next level. 90% of the energy is used by the organism and then eventually lost as heat. So think cellular respiration in the plant, cellular respiration in animals. The animal is using energy as it's taking it in. So only 10% of the energy actually gets passed on to the next trophic level. Okay, so 10% moves up, 10% moves up, 90% is lost. The same thing happens when we talk about biomass, right? My stupid little box. So you probably recognize producers, consumers. So primary consumers are herbivores, secondary consumers are carnivores and omnivores, and then tertiary consumers are top or apex predators. They exist in ecosystems at a set amount based on the amount of available energy, based on the amount of biomass that's available at that primary producer level. So you can measure the amount of energy, you can measure the amount of biomass, so kilocalories, or the amount of grams of biomass that's available. The 10% rule applies no matter how you're looking at that trophic energy level. It's not screaming, clicking. So 1,000 kilograms here, 10% is available at the next, that's 100 kilograms, 10 kilograms, and 1 kilogram. Okay, so you basically just divide by 10. So 95,000 joules, which is a unit measurement of heat, you're going to lose that. You just move the decimal place. Now you have 9,500. Move the decimal place again. You're going to have 950. One more time, you're going to have 95 joules. It's pretty simple math, guys. So if you can calculate this, take a second in your notes, try to calculate the biomass. What do you think is going to be above and below? I'll give you a second. All right, let's see. How'd you do? So here you have to multiply to go up, right, or go down, sorry, and then divide to go up. All right, so think about this problem. Make sure you jot it down in your notes, maybe sketch an energy pyramid in your notebook. And as we finish up today, remember that whatever you do makes a difference. You just have to decide what kind of difference that you want to make. Have a great weekend, guys. Well, you'll see this Monday, so have a great week.